Hello everyone, welcome back to another video in the LLMs related playlist. In this video, I'm gonna take a crash course on how you can fine tune any LLM of your choice, be it small or big, with the help of a two-stage approach. Without wasting time, let's jump into the video right now. So, before going into the coding part of this crash course, let me give you a theoretical insight of how this two-stage approach would be and should be. See, the thing is, once you get a base model, which is either instruction tuned or it is a pre-trained model, right? For your own custom use case, the first step would be for you to do instruction tuning on your own dataset. Okay. For example, let's say you are doing a question answering model. So what you need to do is take a model, let's say model A, and then you will fine tune it with some question answer pairs, just normal training. Okay. And that stage is known as supervised fine tuning or instruction tuning, because this step will help the model to adhere to your instruction. It will try to follow your instruction based on the dataset or data provided. Then the model is following your instruction, but the response is not that good. Okay, it is able to understand the question, it is able to understand the instruction, but the output is not of our desired format, like how a ChatGPT or Google Bard gives, or even Claude for that matter. So for that, what you need to do is you need to do another stage of tuning, which is known as preference alignment. So for preference alignment, there are a lot of techniques available in the market right now. There is RLHF, there is DPO, KTO pair, IPO, which is from Google. So yeah, there are a lot of methods like this, but the most common method is DPO and RLHF. RLHF is used in models like ChatGPT, Claude, and so on and so forth. But DPO is kind of a cost efficient replacement for RLHF. Okay, it also does the same process of aligning your model's responses to your preference. And in this video, I'm going to show you how you can do both of these steps for a given model for a custom use case. For example, here I'm considering a chatbot use case, and I'm going to show you how to create a model to chat with you based on this two-stage approach. Okay, so now let's go on to the coding part. As you can see here, I'm just using Google Colab, which is free version. Okay, it is T4, which is a free version, which means you can also replicate whatever I have done in this video. All right, so I have also given the notebook link in the description. Please maybe have it on your side and try to execute it alongside with me in this video. So the first step for you would be to do installation of the dependencies. Okay, let's put it here, installing dependencies. Okay, so in that we would need transformers. Take this specific version 4.37.2 because in Google Colab they are using an old version, and for you to replace that you would need to specify the version, and then install TRL, which is Transformer Reinforcement Learning Library, in which you have your supervised fine tuning trainer and trainer for DPO or else the preference alignment. Okay, and PEFT for LoRa. I have covered LoRa in detail in our channel itself, so if you haven't seen about LoRa, please check it out. LoRa is a parameter efficient fine tuning method. All right, and accelerate for efficient GPU computation, datasets for manipulating data so that it is following the Hugging Face Hub format, and it is also connecting to the Hugging Face Hub datasets. And then finally bits and bytes for quantizing the model and training it. Alright, so that is about the dependencies, and you can install it by just running this. As you can see here, it has installed all of these, and then the next step for you would be to do notebook login. Alright, so in that, if you run this, let me run it here. Alright, yeah, as you can see here, now the dependencies are installed, and here if you see, there is an existing installation of 4.35.2 and that is replaced by 4.37.2, which we have installed right now. Alright, so that's about installation. Now for you to know how to do notebook login, so for this you need to have a Hugging Face token For that, you need to create an account. All right. So here I have created n number of account. So for that, what you need to do is to create your own token. Click new token, rename it like some name, and then put it as role to be right, and then click generate token. Okay, and then you will have something like this. Click your token, decide token, and then put it in here. Okay, and then click login. All right. But nowadays it is also better for you to have it in your Google Colab secrets itself. Here you can see there is a secrets key, right? In that, if you click, it won't be here like this for you. Click add new secret and then name it as hf underscore token and put your value here like this, right? hf underscore token, and then the same value which you copied there, put it here, and then give access. Okay, for this to give access, you can give it like this. But here I have already configured the secrets, so I won't need that. All right. So now for the first step, which is to do instruction tuning, which is supervised fine tuning. All right. So for this, I'm having the following inputs. We need torch, load dataset function for us to load the dataset from Hugging Face Hub, and dataset class because we won't work with Hugging Face datasets for pre-processing. So we'll make it as a pandas data frame, and then again to convert it into Hugging Face dataset and all, we need dataset class. All right. And from PEFT, we'll be importing LoRa config, auto PEFT model for Cos LLM, and get PEFT model. In this, the most important inputs are LoRa config and get PEFT model, because get PEFT model will create your parameter efficient fine tune model by attaching the LoRa adapters to your model, and the config for LoRa adapters are provided by LoRa config. All right. And then we have transformers import, in which we have auto model for Cos LLM, auto tokenizer, training arguments, and then bits and bytes config if you want it. All right. Next we have SFT trainer being imported from TRL. This is our trainer. All right. And then we have accelerator for, like I said, to efficiently use GPUs and all. And then we have OS. Okay, these are some imports which is required. All right. So let's see the config later. Once we go through the code simultaneously, we'll see the config. All right. So these are the imports which is required for instruction tuning. So here you can see I have created a class for fine tuning with SFT, and similarly I have created a class for DPO. All right. This class can be used for any model. All right. Be it Tiny Llama or Llama 270 billion or Mixtral or any other model of your choice. The process and the code is going to be the same, which means this is kind of your template to fine tune any model. Obviously, you need to edit the parameters, but even these default parameters will do good. All right. Sorry, I have cold. So yeah, let's go into train SFT. You see, for any training of model, we'll need two things, right? We'll need the model, and then we'll need the dataset. We are assuming in this trainer that we have created the dataset, which we'll do later. All right, because this is, like I said, the template. In template, we can't say like dataset will be like this, right? So we are creating dataset separately, and here you can see I'm taking data and config as parameters, because here none of the parameters are set at runtime. Okay, all are set at the config itself, so that whenever we want we can edit the config, and then it will become like whatever we want it to become. So here if you see in create trainer function, right, the first, this is the function which we'll use at the last. All right, which is train and save model. In this, the first step is to call the create trainer function. So let's go in there, and then in there I'm calling load model tokenizer. So let's go into load model tokenizer. All right, now we have the data and configuration. So what I'm saying is, let me call the model first. Okay, and for model checkpoint, where I need to go? Yes, you got it right. We are gonna go into the configuration. Okay, here for model checkpoint I have given tiny llama 1.1b chat v chat -v 1.0. all right, Let's put it here. And as you can see here, here is a model. All right. And we are using this model, which is very less in size actually. It is just 2.2 gigs. And even if you want, you can try lesser size models, or you can try 5, because there are a lot of people who are asking me how to fine tune small models like Tiny Llama, 5, 2, and so on and so forth. And some people are asking like how to fine tune Mixtral, how to fine tune Llama to 70 billion, and so on and so forth. For every model which people have asked me, guys, this is the code. All you need to do is change the model checkpoint, and for you to run it in Google Colab, obviously you need to edit some other parameters. But some models you can't even run it in Google Colab. For example, Llama to 70 billion, Llama to 34 billion, Mixtral, these are not possible, but for Mistral, yes, till that you can run this in Google Colab. Alright, so here for model checkpoint, we are having Tiny Llama hyphen 1.1 billion, chat v 1.0. Alright, next in that we are needing a parameter known as load in 4-bit. Okay, we are doing something called QLoRa training. Okay, where it means that you are quantizing your model and you are applying LoRa on top of it. So here for quantization, we are quantizing it in 4-bit. All right, it is in 4-bit. So what I'm saying is, okay, load in 4-bit, I'm giving it as true. All right, and then for device map, it means that the layers in the model, it should be assigned to which device. Okay, let's say you have multiple GPUs, because it's not always we'll use Google Colab, right? Some people might use their office servers, some people might use their local GPUs, and you might have more than one GPU in your hand, and you will try to use all those GPUs, right? It is hard to configure it by yourself, because let's say you have 32 layers in the model, and each layer has its own heads and all. So to configure it specifically for each device and doing it perfectly, it is hard, and that is where Accelerate comes into the picture. So whatever we need here, Accelerate has already done, and for that what we are doing is, any layer, Accelerate will provide a local process index. Okay, it will try to map the device by itself. You need not do anything, and that is why I said we need accelerator. All right, next for torch dtype. So what torch data type we are going to use is that we are going to use torch float 16. Okay, float 16 is a very good precision for us to work with. It is known as mixed precision training, and this precision is more than enough for most of the use cases. Alright, then what we are doing is, we are setting the use cache of the model's config to be false. Okay, so why is this needed is because we are setting the model to be trained in training mode. Usually it will be set as true, okay, which means it will use its cache for inference. Okay, we are not doing inference, right? So we'll set it as false, and then to replicate the pre-training training performance, like to not lose any pre-training training performance, we'll also set pre-training TP to be 1. And then we are preparing the model for k-bit training. Okay, like we are doing it in k bits, which is 4 bits here, and for that we are having this function called prepare model for k-bit training, in which you need to pass your model. All right, so now we are again checking if we want to use LoRa, because like I said, people might not need LoRa because they might think, okay, we'll do full fine tuning, we'll fine tune all the parameters, we have the resources. So what you can do in that case is set this use LoRa parameter to false. Okay, but if you set use LoRa to be true, the LoRa adapters will be attached. All right, so here it is true, which means there is a function called self.prepare LoRa model, which will be called, and that is here. Okay, in this I am creating a LoRa config, which will take the LoRa rank, which is set to be 16 here. LoRa alpha is 16, LoRa dropout is 0.05, bias is none, and task type is causal LLM. So here you can see that for R I'm providing 16, LoRa alpha from config we are also providing 16 there, LoRa dropout is 0.05, bias is none, task type is causal LLM. And if you are going to fine tune models like probably Plantify or something like that, you need to replace auto model for causal LM to auto model for seek to seek LM, and then change this task type to from causal LM to seek to seek LM. The only difference here is target modules. All right. For target modules, what happens is you can't provide a constant target modules always. So for that, what you need to do is go to your model, which we have opened here already. See the configuration. Right? If you know the configuration already, which is let's say llama for causal LM. For llama, we already have seen a lot of times that it is going to be Q projection, V projection, K projection, gate projection, up projection, down projection, and so on and so forth. All right. If you know it, then it's well and good. You can have your own target modules. But let's say you are using another model. Okay. Big code. Let me try that. For example, in the star coder, right, they would have used a different configuration. All right. So let me show about that also. Here it is GPT big code for causal LM, right? So here it won't follow the configuration which we have spoken about just now, like Q projection, V projection. That name for the layers wouldn't be used. So which means adapters won't be attached and you're not gonna train anything basically. All right. So what you can do in that case is go to your model and search for this specific file known as pytouchmodel.bin.index.json. Okay, if you can find it, it is very good. If not, first call your model into some Google Colab cell and then do print model. Okay, in that you will be able to find the names of the layers and then you can choose accordingly. Don't worry, I'll also show how you can do that. All right, but this is easier, so let me say about this first. So in this is weight maps. Okay, so here they are having an attention module in which they are having a layer called C attention, C projection, and they are having a linear layer LN1, LN2, and then they are having in a multi-layer perceptron class they are having CFC and C projection. Okay, these are the layers present in star coder. All right, these are the layers present in star coder. So for you to understand this, what you need to do is see where there is written as bias, weight and all. Okay, and see the name previous to it. Like for example, here it is C attention, right? That will be the module name, which is your target module. All right. So now you're thinking, Vasanth, this is too hard for me. Give me some simple way. Okay. So let me create a dummy cell here. From transformers import auto model for causal LM. Model equal to auto model for causal LM dot from underscore pretrain and the model name. All right, which is here as star coder. Let me see the model size. Okay, it is too huge. So let me take a similar model which is less in size. For example, here it is a 1 billion model Santa coder, which also follows the same architecture. Okay. So let me take that and we need to print the model. All right. So let's do a time lapse. So here you can see the model is now printed and these are your modules. Okay. In there it is given, right? Module list, attention. In attention you have C attention, C projection, attention dropout, residual dropout. Usually we won't consider dropouts. Okay. But consider the other layers. All right. Mainly your attention and your linear layers. So here you can see it is C attention and C projection and CFC and then C projection. These are the layers which you need to consider. All right. And this is how you get the name. So here if you do tiny llama, you will have Q projection, V projection, K projection and so on and so forth. And I have chosen only Q projection and V projection. But this is how you will try to see the model name and the model's target modules. Whatever model, it will be the same approach. All right. So now we have configured our LoRa adapters. So the next step would be to create the LoRa model by attaching these LoRa modules to the model, which you can do by calling this getPef model function, which will take two parameters, which is model and then its config. Okay. So here you can see I'm doing everything in self parameter itself so that everything is updated by itself. Like we need not call it as a separate variable and then pass it again as a parameter. Okay. Everything is done in self itself. Okay. self.model is equal to get bef model of self.model comma self.lora config, which will try to attach your LoRa adapters. Okay, now we have our model. So next step would be to create your tokenizer, because we need to tokenize the dataset. Okay, within SFT trainer, the good thing is you need not tokenize it prior to your training. Okay, it's not like previously you need to tokenize it and then you will train it. No, it will try to tokenize it at runtime, which is a time saving process, but for that you need your tokenizer, right? So for that we'll also take the model checkpoint name from the configuration and call auto tokenizer. But the thing here which is very important is setting the path token to be EOS token. Okay, please don't forget this step, so that it won't be padding up till the end and it will stop the generation. All right, next we have set training arguments, because we have our model. Okay, and here if you see in this create trainer, right, the first step is to load the model and the tokenizer, which is done already, and obviously we are checking if the LoRa adapters are attached. For that we are calling this function called model.print trainable parameters, which will print the trainable parameters, because in LoRa what it does is it will try to freeze all the parameters which is there in the base model, and it will enable only the LoRa adapters to be training, which will be just 1% or 2% of the whole model, right, which is very less, but it will give the same performance, almost close-ish. And here if you see, we are passing the model, and for trained dataset we are passing the data. If you have an eval dataset created, you can also pass that here by having it as eval underscore dataset data. All right, but I don't have it, because my convention of training is usually when you do evaluation, right, it will take a long time for you to do evaluation because it doesn't CPU. So what you can do is save a checkpoint at some point of time and then try to do it offline or separate in a separate process. Okay, don't disturb your training. When you do long training, it will be very irritating actually, because let's say you do 1,000 steps of validation, right, it will take so much time. So yeah, I would prefer not to do evaluation at the training loop itself. But yeah, if you are interested, you can also do it as eval dataset and then provide your data. And then we are needed to provide the LoRa config also under the name PEF config, because in PEF itself there are other methods like prefix tuning, p-tuning, and then we have IA3, which is a very good method which is being stated till now. All right, but we are following LoRa, so we are providing the LoRa config. Next, the important thing for you to pass is the dataset's text field. Which is the dataset text field? Which is the data like I should consider the column name here. So for that we need to go to the config train column name, and where is it? Train CLN name. I'm able to find actually. Yeah, here it is. Train CLN name I have provided as text. Okay, always it is needed for you to have it as like a simple name. Okay, text is a common name, right? So keep it as text, but all your values should be under one column known as CLN, or like whatever name you have it, because causal LLM is kind of a completion, and for completion you will have always only one column. All right, next we need to have set training args, which is a function here. Okay, so let's see the function, because this is the function we use to set our training arguments. All right, here is our training arguments, where we are for providing values for the following parameters. The first parameter we are providing is output directory in which you want to save, and then we have our train batch size. So for each step, how many datasets should be processed, that is your train batch size. And then we have our gradient accumulation steps, which means that so in how many steps do I want to do back propagation. Okay, so that is gradient accumulation steps. Let's say you have 10. Okay, so till 10 forward steps the gradient will be accumulated, and then it will do one step of back propagation. It is computationally it will like take a lot of space, but it will take lesser time. Okay, so that is the advantage of gradient accumulation steps. Then you have optimizer. Here we'll use a special type of optimizer which will obviously work well for quantized models, but generally an optimizer is one which will optimize your model's learning. Okay, it is the one which is making the back propagation and then like going towards the global minima. And then we have our learning rate, the rate at which it wants to learn. And then we have our learning scheduler type, learning rate scheduler type. Next, we have the save strategy. So how you want to save? Do you want to save in steps? Do you want to save in epoch? I am a fan of saving it in epochs, but when you do large training, like bigger training, you want to go for steps. Okay. And then there you would need another parameter known as save steps, where you can provide the number of steps at which you want to save. All right. Next, we have our logging steps. So in how many steps do I want to log? In logging steps, what it will do is it will try to compute the training loss at that time. Okay, let's say I have 100 steps. So at the 100th step, it will try to log the training loss at that point of time. And then we have the max steps. When you're doing training, please do comment this. All right, I'll have it commented. So here, this is provided because when you do very large scale training, okay, let's in millions, but you're not like having the, how can I say, like leisure, probably you're not having the leisure to do it for the millions, okay, but you want to load the data, you don't want to sample it or something like that, like you want to just provide it, but you want to stop it at some point of time. Okay, so at that point of time, what you can do is you can set the max steps to be some value. Okay, so here if it is 1000, it will stop in 1000 steps. Okay, 1000 steps. So if you have provided as batch size as probably 8, then it will have seen 8000 samples and then it would have stopped, be it millions or trillions, but the steps will be only 8, like the samples it has seen would be just 8000. All right. So next we have FP16, which is set to true. Okay, don't worry, I'll say the values by showing the configuration, but right now I'm saying that like the FP16 value is true because we are training it in float 16, right? The training also should happen in mixed precision, so we are setting float precision to be 16, and then push to hub, which will provide a value of either true or false. If we provide the value to be true, then the model will be pushed to the Hugging Face hub. And if you are working for an organization and the model should be in private, right, then it should be in it would be in false. Okay. Now let's see the values. All right. Output directory, I have given it as SFT tiny chatbot because we are doing SFT stage, right? So for that, I'm keeping it as SFT tiny chatbot. And batch size, I'm keeping it to be 1, as simple as that, but it can be moved up a bit too. And then I have provided gradient accumulation steps to be 1 because it is collab, it doesn't have that good memory and all. So it is good to have it as 1 itself. Next we have optimizer, for which I have provided the value as paged AdamW 32-bit optimizer. Okay, so this optimizer is what will make your training like very good. Okay, normal AdamW is very suitable for normal model training, but paged Adam optimizers are usually very good for your quantized training. Okay, but there are some other optimizers as well, like 8-bit, 4-bit and all. Probably you can also experiment with that. Right, then the learning rate, a good starting point, like to set the max barrier, right, it would be 2e minus 4. And then we have, like, when you provide learning rate as 2e minus 4, what happens is like that is the maximum learning rate. It will try to go lesser, let's say 2e minus 5, 2e minus 6, and like it will be like the maximum thing, and then you can go any much lesser than that, which the model will decide while training. Okay, sorry, not the model, the optimizer. Here you can see the scheduler type, when we should change the learning rate. Okay, and we are following a cosine learning rate scheduler type. And like I said, we have provided the save strategy to be epoch, logging steps to be 100, training epochs. Like what you can do here is, I'll also add it here. I don't know the exact name actually. I don't think it is provided here. Train epochs SFT trainer. Let's see. I think it is in training arguments actually. Training arguments. Yeah, it is num train epochs. I just want to keep a remembrance of the name. I'll put it that also. Oh yeah, I've kept it. I forgot. Sorry guys. It is num train epochs. I have provided as 1. Actually, by default it would be 3. I've kept it as 1. Okay, so num train epochs is 1, which I didn't say. Okay, but when you keep max steps, it will be overridden. Okay, it will be stopped at for example 250 steps here. Since I have kept batch size as 1, it will see only 250 samples. This is just, like I said, a demo training, right? Like when you do some real training, it would be like, correct for you. And then we have FP16 to be true because I want to train in mixed precision. And then we have push to hub to be true because I want to push the model to the hub so that I don't need to save it in local. All right. So that is about the training arguments. You didn't like, you can comment the max steps if you want. All right. Next, we need to go on to the continuation of SFT trainer. We have provided the model, dataset, the training column name, training arguments, tokenizer, and then we have something called packing. So what happens in packing is that, let's say you have a max length of 1024, but the dataset sizes are probably 768, 256, something like that. It will try to pack the sequences together with a separator token so that it will be always 1024. There will be no path token and all. Okay, so at the cost of one step, you will see two samples, something like that. But I don't prefer using packing, so always I keep it as false. And then max sequence length, we have provided max sequence length to be 512. All right. Here you can also provide another value known as Neptune underscore noise underscore alpha. Okay. Self.config of Neptune underscore noise underscore alpha. All right. So what happens in Neptune is that while you are training, right, in embedding layer, some noise will be added. All right. And it is set to provide from 2 to 3% of accuracy to till 7% of accuracy improvement. All right. So that is stated in the paper known as Neptune. So if you are interested, you can also check it out. But like here, the noise alpha is set to be like the best value is set to be 5, and we are setting the same. Okay, it is 5 here. All right. Next, the trainer is done. So create trainer is done. Next, we need to call the train function. Okay. So if you call the train function, it's going to train, and then you will call the save model function to save the trained model, which will save only the adapters. And when you call it, like you can combine it. Okay. So here we have the output directory where you want to save, and the tokenizer, which is also saved in the output directory. Okay. So that is about SFT training. Probably, if you like feel like, okay, Vasanth, I'm not clear here, please let me know in the comment section. I'll be more than happy to help you out, because you might face some errors, right? So whenever you face some errors, let me know. I'll help you out with that. And then we have the create data function, because like I said, we need model, training loop, and then data. Obviously, we have done our training loop, we have done our model, but there itself we needed a data, right? Because we are ready with the configuration, which is one parameter, but the data set is not ready. So we'll do that first. All right. So I'm using a data set known as alpaca, which is for data, like chat data. Okay. In that we are calling the training split alone. So here I'm just taking the 5,000 samples. Probably you can also keep it as 700, but still it wouldn't make any difference because we are going to run it only for 250 steps. All right. So here, like I said, the model expects, or the training loop expects to have it in the single column name, which we have provided in our case to be text, right? So here what I'm doing is there are 3 columns in the data actually: input, instruction, and output. Let me show you the data. Yeah, here it is. Okay, here you can see instruction, input, and output. Okay, probably they have also provided text, but I didn't, when I wrote it, when I wrote this code, this text column was not there. So we have the instruction, input, and output, but it is also for good. Like you always might not have a single column. So what you can do is you need to find a balance. So here you can see you have give 3 trips for staying healthy, and you don't have any input, and then you have your output some values. Okay, where you want to find these balances, let's say here you can see evaluate this sentence for grammar, spelling, and mistakes. That is your instruction. He finished his meal and left the restaurant. Okay, this is your input, and then your output. So it is going to be instruction and then input and then output, right? So instruction and input are provided by human, and output is provided by the assistant, right? So here we are keeping it as human and then instruction, and then the input, and then we are providing the output with the assistant tag before it. All right. So when you apply this, there will be a new column created as text, and then you'll create a data set from those pandas data frame by calling the dataset.from pandas. Okay, and once you pass that as parameters to the train and save model, it will train it. Okay, so it will train well. You can train for longer time and it will work. Okay, for, like I said, any model. All right, now like I said, you have done the SFT stage. Now it is following an instruction, but the output is not satisfactory. Like the format can be better, especially when it comes to chat. The dataset might have some harmful words, harmful content. To remove that and to make it like, okay, I'll speak only good things, I will not speak any bad things, something like that. In my case, probably in your case, if you are going to do some information extraction and you want to generate some JSON, the JSON structure might not be good. To force it to generate some JSON structure, you can follow this method known as preference alignment, wherein there are three popular methods, which is DPO, IPO, and KTO pair. And DPO was the predecessor, like it was the root method, and then IPO and KTO pair were some modern methods which came out of DPO. So if you're wondering how DPO works, again, I've made a detailed separate video of DPO. So if you haven't checked it out, please check it out. The links for LoRa, DPO, research papers and all are given in the description. So yeah, you can check it out. Here also the imports are going to be similar, okay, except this trainer, which is DPO trainer. Okay, and then we have our model checkpoint to be changed. Okay, here I will tag it as Vasanth SFT Tiny Chatbot because we pushed it to the hub and the name was SFT Tiny Chatbot. And here you can see I've changed the LoRa rank and alpha to be 8 and 8 because I was unable to load in 16. All right. Then others gonna be same, but here there will be some difference. There we had it only till Neptune noise alpha, right? So after that there will be some changes here, which I'll say now. Right. So here you have your LoRa model being prepared, you have your load model tokenizer, but here we have model as well as model reference. Okay, see, the idea in preference alignment is that one model will train the other model to focus on the generation of output, okay, or the results. Here the model will be same. In RLHF what happens is usually you'll have a separate reward model to do this. But here in DPO and other preference alignment methods, your self model, like whatever model you are training, that model itself will force the other model to generate accordingly. So here you can see we have model and model ref, which will also have the same parameters. Okay, but we'll do this use cache and pre-training training performance and prepare model for KB training, everything only on model, because we are going to train the model which is self-taught model only. Okay, the model in model ref, it's just for the reference for it to provide some penalizing and train, okay, accordingly. So for that we have model reference also, and then we have prepare LoRa model, we are calling the tokenizer, and the training arguments are going to be the same, like it's not going to differ. All right, the thing which is going to differ here is the trainer, okay, which is something very different from the last one. So here we are calling the DPO trainer, where you need to provide the model reference model, and then your training arguments, data, tokenizer, that is all there. And beta is the learnable scaling parameter, or like it is a parameter which will adapt the rate of learning. Okay, it is similar to learning rate and for each method it is set to have a specific good value. For DPO, the ablation study states that it is 0.3 or 0.4, probably even 0.6 to some extent. For KTO pair, it is 0.1, and IPO, it is 0.01. Okay, so whenever you change the method, you can also change the beta value. Please don't forget that. Then we need to provide the most important parameter in DPO trainer, which is loss type. In loss type, there are different losses. So let me show you the source of DPO trainer. Okay, so here you can see I'm going into the trainer. and let's go into the DPO loss function, right? So here you can see there are different types of loss, and here you can see there is hinge loss, there is sigmoid loss, and there is that other things like here you can see, right? Sigmoid, hinge, IPO, KTO pair. Here it is KTO pair. Okay. The thing is, each are from a different paper. Hinge is something I haven't explored yet, but IPO, KTO pair, and sigmoid is your DPO loss. Okay. So these three methods, for those, what you need to do is, if you are going to use DPO, provide the value of loss type to be sigmoid. And if you are going to do IPO, provide it to be IPO. And for KTO pair, you can provide it as KTO pair. All right. And this is the loss function. And yeah, you are providing that loss function here to your model. Okay. And then we are setting the max length, which is the total length. Okay. Sorry. It is the total length, and here we are setting it to be 768. But the input length which I am providing here is 512, and the output length which I am expecting from the model to be maximum is 256. Okay, so it is total 768. Here it expects an auxiliary parameter because this trainer is common for both causal and sequence to sequence model. So to know if it has decoder or not, there is a parameter known as isEncoder decoder, and for isEncoder decoder we are setting it to be false. So here if you have Flantify XL or Flantify UL2, these are all pretty huge models. Okay, what you need to change is, you need to change the model checkpoint, you need to change your target modules, and then change from auto model for causal LM to auto model for seek to seek LM. Others are going to remain same, and this encoder decoder to be true. But if you are going to change for some larger models that is in causal LM itself, you need not even worry about anything. Change the checkpoint name, and then yeah, like adapt your training parameters alone, like the training arguments. But otherwise everything is going to be same. But here the thing is different. You need not provide something called dataset text field. That is not needed here. Okay, because it requires a specific format. There it was not required. Okay, if you give an output column or an input column, it will focus on that column. Okay, but here it won't be like that. It will have 3 columns which is required by itself, which is prompt, chosen, and rejected. Prompt will be your input to the model. Chosen will be the expected output from your model. Like, let's say I'm asking, let's say tell me 10 bad words. Okay, it should not say the bad words, right? So if it says the bad words, it will be the rejected response, and if it is saying like I'm a bot, I can't say some harsh words or something like that, that will be the chosen response. So for this, there is a dataset known as HHRLHF, which is from Anthropic. Okay, I've taken this datasets, and here you can see there is only 2 columns, chosen and rejected, where there is no prompt. And here you can see there is assistant here, right? There is human, and then there is assistant here. So what I'm doing is, I'll split the assistant from the human. Okay, so I'm providing, see here, in chosen I'm applying something called split. So it will try to split the sentence from assistant and the 0 of that, like before assistant everything will go to prompt. Okay, after assistant everything will go to chosen, where we'll also add the prefix assistant, because once you split it, the name assistant will be gone. All right, so in rejected column I'm applying the same, so that it will have the rejected values, and I'm sampling only 1000 samples, so that we can, obviously we are going to run only for 250 steps, right? And then if you call the train DPO function, it will train. All right, so again you will push it to the hub. So that is how your 2 steps will be completed. Now you can think, Vasanth, yeah, you have done the training, but if it is not good for any inference, what I'm gonna do about it? So for that, what you're gonna do is, you're gonna call a function called, or the class name called AutoPef model for causal LM, which has your model name from the hub. It will try to attach the model LoRa parameters together, and then it will provide the input to you. So here what we are going to do is, we are going to take that model and we are going to give it to transformers pipeline. All right, so we are following some kind of input format here, like provided from them itself. Even you can provide it as human and assistant also. Okay, I'm just following what is given in Hugging Face. And here if you see, I have asked how many helicopters can a human eat in one sitting. A human can eat about 4 to 6 servings of helicopter food, typically made of meat, cheese, vegetables, so on and so forth. Okay, these are some helicopter food it seems. So yeah guys, and that is how you do a custom model for your own use case. And if you have any doubts, let me know in the comment section. I will help you out. Or if you have big doubts like to be a separate video, that also let me know in the comments. I'll make a separate video. So in this video, I have shown you the two-stage approach in which you need to follow to create your own model. So there are some other parameters you can play with. For example, in training arguments, you can set a value to report to be tensor board, so that you can save the losses to the tensor board. Because when you do a long training, you can monitor the tensor board logs. Alright, so yeah guys, that's it for this video. I hope you all like this video. If you all think that I have got something useful in this video, please hit the like button, share it with your friends, and provide some comments, and that will help me to reach more people like you all. I'll see you all in the next video guys. Until then, cheers.